Assalamu alaikum, dear students. Welcome to the second session on NMR spectroscopy. Today we are going to discuss a very important topic. So this lecture and the one after it, they are very important for you guys to understand the basic principle behind NMR spectroscopy. So once you understand the basics of NMR, it will be easier for you to understand how to interpret the spectrum and how to get maximum information from the spectrum. So I would suggest that you don't skip and watch this lecture till the end along with the next couple of lectures so that you get a holistic view of what NMR spectroscopy really means. So let's see what we are going to discuss today. We'll be talking about the basic principles of NMR spectroscopy today, and we will also discuss how an NMR signal is generated. What are the events or what are the steps involved in the generation of an NMR signal? So let's begin. Nuclear magnetic resonance spectroscopy, as we discussed in the first lecture, it deals with the study of the nuclei or the study of the behavior of the nuclei under the influence of an external magnetic field. But which nuclei? Only those nuclei which have some certain amount of spin are NMR active. Or you can say that we can study only those nuclei in NMR which have certain amount of spin associated with them. Those nuclei which do not have any spin will be NMR inactive, or in other words, we cannot study their behavior in NMR or under the influence of an external magnetic field. Now, which are those nuclei which have some amount of spin? So those nuclei which have an odd mass or an odd atomic number will have some amount of spin. Atomic number is the number of protons that you already know. So if a nucleus has odd number of protons, it might have some spin. Or if its mass is odd, mass number is the sum of the protons and the neutrons. So if the sum of the protons and the neutrons is odd, then that nucleus will also have some amount of spin. So those nuclei which have an odd atomic number or odd mass number will have spin. And these are the nuclei which can be studied in NMR spectroscopy. So this is the basic equation on which NMR is based. Mu is the magnetic moment of the nucleus that we are studying. That is equal to gamma I H. H is the Planck's constant, as you all know. I is the spin of the nucleus. So from here you can see that if I is equal to 0, magnetic moment will automatically be 0. Magnetic moment is basically, you can call it as a response towards a magnet. So if I is equal to 0, mu is equal to 0, or magnetic moment is equal to 0. While gamma is known as the gyromagnetic ratio. Or in some texts you may find it written as magnetogyric ratio. Now this ratio is a characteristic property of every different type of nucleus. So for example, proton will have its own gyromagnetic ratio, carbon-13 will have its own gyromagnetic ratio. Similarly, other nuclei like nitrogen, phosphorus, they will have their own gyromagnetic ratio under the influence of a particular magnetic field. And it's a constant, so it will not change with the change in the strength of the magnetic field. So gyromagnetic ratio also affects the overall magnetic moment of a nucleus. So these are some of the nuclei that we may or may not be able to study in NMR. So we have the proton numbers and the neutron numbers written for all of these nuclei. So if the proton number is even and the neutron number is also even, then the spin quantum number is equal to 0. And as I told you earlier, if spin is equal to 0, I is equal to 0, then the nucleus cannot be studied in NMR, or it is NMR inactive. And the examples are carbon-12 oxygen 16, and sulfur 32. So these three nuclei cannot be studied in anima because they have even number of neutrons as well as even number of protons. In other words, their atomic number and mass number both are even quantities. Like for example, carbon 12 has 6 protons and 6 neutrons in the nucleus. So the overall mass number is even as well as the number of protons is even. So it cannot be studied. If a nucleus has odd number of protons and even number of neutrons, then the spin quantum number is half for nuclei such as proton or protium, fluorine 19, and phosphorus 31. So hydrogen, or protium has an odd number of protons, that is, it has only one proton in the nucleus and there are no neutrons in the nucleus. So the neutron number is even, the spin is equal to half. So that means that proton or protium can be studied in NMR. If the number of protons is odd and the number of neutrons is even again, but the spin is equal to 3/2, examples of such nuclei are boron 11, chlorine 35, and bromine 79. If a nucleus has even number of protons and odd number of neutrons, again, if the spin quantum number is half, example for this type of nucleus is carbon 13. Now carbon 13 has 6 protons but 7 neutrons. So the mass number is 13. That means it has an odd mass number and it is NMR active. The spin quantum number is half. Similarly, we have these different combinations for nuclei having different spin quantum numbers. For example, iodine has spin is equal to 3/2. So iodine 127 is NMR active. Oxygen 17 has a spin quantum number equal to 5/2. So oxygen 17 is also NMR active. And here we have deuterium along with nitrogen. So deuterium having spin quantum number equal to 1 is also NMR active. Sometimes I hear from students that deuterium is NMR inactive. Deuterium is NMR active because its spin quantum number is 1. But it is different from proton in some aspects. Now if you look at this table, I have written this row and this one in a different color. That is to indicate that we have hydrogen here or proton here and carbon 13 here. And we will be focusing on these two nuclei because these two nuclei are the most studied nuclei in NMR. Of course, you can study the rest of the nuclei as well, but we're not concerned with those right now. We will only be talking about proton and carbon 13. And luckily, they have the same spin quantum number. So whatever we study for proton will also be applicable to carbon 13. So whatever events or steps we are going to study after this, they are equally applicable to proton and carbon 13 because they have the same spin quantum number. But of course, they are different nuclei, their gyromagnetic ratios are different, their magnetic moments are different, their natural abundance is different. So they are, of course, different from each other in some aspects. The basic principle of NMR applies equally to both proton and carbon 13 that we will see in a moment. So a nucleus that has some spin quantum number, there are certain spin states associated with it as well. So the spin states can be calculated from this equation, that is 2i plus 1. I is the spin quantum number. So if the spin is half, 2 into half plus 1 is equal to 2. So both for both proton and carbon 13 having spin half, 2 spin states are possible. And that is why I say whatever we study for proton is equally applicable to carbon 13 because luckily they both have the same spin quantum number and equal number of spin states possible under the influence of an external magnetic field. Similarly, if we talk about deuterium, which has spin equal to 1, so 2 into 1 plus 1 is equal to 3. So deuterium has 3 possible spin states, or nitrogen has 3 possible spin states. Similarly, you can calculate the number of spin states or the number of possible spin states for every different nucleus from this table. Now we are going to discuss the steps that are involved in the generation of an NMR signal. And this is very important. And again, I urge you to watch it till the end. Do not skip in between so that you get an idea of every single step, every small step involved in the generation of NMR signal. And it will help you a lot in the lectures to come when we will be talking about the positions of these signals. We will be talking about the multiplicities. We will be talking about other things. So pay attention, please, and listen to it carefully. So what happens when we turn on the magnet? Or what happens when we place a nucleus inside a magnetic field? So we have a spin-active nucleus, or any nucleus that has some amount of spin associated with it, and we place it inside a magnetic field. What happens to it? 2 things happen. The first thing is that it arranges itself in all possible orientation. All possible orientations mean that the nucleus arranges itself in all possible spin states. I just told you about the spin states, that spin states can be calculated from the equation 2i plus 1. So according to the spin quantum number, or depending upon the spin quantum number, you can calculate the number of possible spin states. So for proton and carbon-13, the spin states, the number of possible spin states are 2. For deuterium, they are 3. So the first thing that happens when you place a spin-active nucleus inside a magnetic field is that it arranges itself in all possible spin states. And this is what happens. So we have a nucleus which is not under the influence of any magnetic field. So there is no magnetic field. And you can see that these nuclei, which we have shown here as a vector, are oriented in different directions, or you can say that they're randomly oriented. But as soon as you turn on the magnet, they arrange themselves in all possible spin states. And now you can say that they are organized. So for a spin half nucleus, there are 2 possible spin states, and you can see that some of them are pointing up, others are pointing down. Here we have B naught. B naught shows the strength of the applied magnetic field, and we have shown its direction upwards by default. So everywhere in the text, everywhere in the literature, you will find this B naught pointing up. Actually, this magnetic field is surrounding the nucleus from all directions. So you can see that B naught is pointing up. Some of the nuclei are pointing down, others are pointing up, which means that some are arranged or oriented along the direction of B naught, others are oriented or aligned against the direction of B naught. So some are parallel to B naught or external magnetic field, others are against the direction of B naught. But this is not the only thing that happens to a nucleus when you place it in a magnetic field. The second thing that happens is that it starts to precess with a particular frequency. Now, what is precession? Precession is a special type of movement. It's just like a top, a revolving top just before it falls. So you would have seen that when you spin a top, it moves faster, and before it's about to fall, it starts a wobbling movement. You can see that it moves like this before it is falling. And this type of movement is known as precession. And this precession happens with a particular frequency. That frequency is known as the Larmor frequency or the precessional frequency. So that precessional frequency is written here as omega, which is equal to gamma B naught. Gamma, again, is the gyromagnetic ratio that is independent of the applied magnetic field, and it's a characteristic property of every different type of nucleus. So for example, we are talking about proton and carbon-13. So proton has a different gyromagnetic ratio than carbon-13, which means that under the influence of the same strength of applied magnetic field, the Larmor frequencies of proton and carbon-13 would be different because they have different gyromagnetic ratios. And that is one of the differences that I was talking about in the previous slide, that proton and carbon-13, although the basic principle of NMR is applied in the same fashion to both the nuclei, but they have some differences, and this is one of the differences. So under the influence of the same strength of the applied magnetic field, the Larmor frequencies of proton and carbon-13 would be different only because they have different gyromagnetic ratios. And you can see that we can show these nuclei in such a way to show their precessional movement. So these nuclei, some are pointing up, others are pointing down. This is again the direction of B naught. So you can see this nucleus pointing down, this one is pointing up, and at the same time they are precessing with a particular frequency, which we call the Larmor frequency or the precessional frequency, represented by omega. This is also equal to mu by 2 pi. 2 pi again is constant, so mu is the frequency. Now let's move on to the next step. Here is a table that shows the similarities and the differences between proton. In fact, this table only shows the differences between proton and carbon-13 under the influence of a magnetic field or in NMR. So we have proton and carbon-13 here. The natural abundance, as I told you earlier, of proton is about 99.9%, and that of carbon-13 is only 1%. So you already know that protium is about 99.9% in nature, deuterium is 0.1%, and tritium, which is radioactive, is even in lesser proportion or lesser abundance. Carbon-13 again is 1%, carbon-12 is almost 99%. So this means that it is easier to find a proton in a molecule than to find a carbon-13. Like for example, you have a chain or a ring of carbon atoms in a molecule, and you're going to analyze it through NMR spectroscopy or carbon-13 NMR spectroscopy. So there is only 1% chance of each of that carbon in the ring or in the chain to be carbon-13. And there are 99% chances of all of those carbons to be carbon-12. But as I told you earlier, that carbon-12 is NMR inactive. You cannot study it in NMR. You cannot see it in the spectrum. You can only see carbon-13. So to find out carbon-13, that's only has a chance of 1%. So that means you need to increase the number of molecules so as to increase the percentage of carbon-13 being present in that molecule. In other words, you might need more quantities of your sample to analyze the molecule in carbon-13 NMR spectroscopy, but for proton NMR, because it's 99% in nature, it's easier to find than deuterium and tritium, so you might need lesser quantities of your sample to be analyzed in proton NMR spectroscopy, or you can easily find protons in the molecule. Next, we have the strength of the applied magnetic field, that is B naught in Tesla. These are the different conditions provided to both protons and carbon-13s, the conditions of magnetic field. And as I told you earlier, that as soon as you turn on the magnet, these nuclei, they start precessing with a particular frequency that is known as the Larmor frequency. So these are the different frequencies under the influence of different strengths of the magnetic field. And then we have the gyromagnetic ratio in radians per Tesla, and that is independent of the applied magnetic field. You can see that the frequency is dependent upon the applied magnetic field, but the gyromagnetic ratio is independent of the applied magnetic field. So you can see here that the gyromagnetic ratio of proton is 267, and the gyromagnetic ratio of carbon-13 is 67. By the way, gyromagnetic ratio is the ratio of the magnetic moment to the angular momentum. So that also means that if we have a higher value of gamma for proton, that means the magnetic moment of proton is higher than carbon-13, which means the response towards the magnet is higher for proton than for carbon-13. And if you compare both of these values, you can see that this value, the gyromagnetic ratio of proton, is almost 4 times greater than that of carbon-13, which means that the magnetic moment of proton is greater than that of carbon-13. Let's talk about the frequencies. So if we provide a magnetic field of 1 Tesla to proton, it will start precessing with a Larmor frequency equal to 42.6 megahertz. As you increase the magnetic field from 1 to 1.41 Tesla, the Larmor frequency increases to 60 megahertz. At 2.35 Tesla, the frequency is about 100 megahertz. And at 7.05 Tesla, it's equal to 300 megahertz. Let's come down to carbon. So at 1 Tesla, the Larmor frequency of carbon-13 is 10.7 megahertz. At 2.35, it's 25 megahertz. And at 7.05, it's 75 megahertz. So for both the nuclei, the Larmor frequencies or the precessional frequencies are dependent upon the strength of the magnetic field. And you can see that there is a direct relationship between B naught and omega, or the strength of the magnetic field and the Larmor frequency. So as soon as you increase B naught, Larmor frequency increases. And that means that when you turn off the magnet, it will stop precessing. Omega is equal to 0. Now let's compare both proton and carbon-13 under the same conditions of applied magnetic field. That is, if you provide 1 Tesla to both proton and carbon-13, you see that their Larmor frequencies are different. This proton precesses at about 42.6 megahertz, but at the same magnetic field strength, carbon-13 precesses at about 10.7 megahertz. If you compare them, again, proton has a Larmor frequency that is almost 4 times greater than that of carbon-13 under the same magnetic field strength. At 7.05 Tesla, the Larmor frequency of proton is 300 megahertz, while that of carbon-13 is 75 megahertz. So again, there's a 4 times difference between the Larmor frequency of proton and carbon-13 under the influence of the same strength of the applied magnetic field. So their gyromagnetic ratios are 4 times different, and their Larmor frequencies are also 4 times different from each other. In fact, the natural abundance of proton is also about 99% greater than that of carbon-13, which means that proton is a more sensitive nucleus than carbon-13 when it comes to NMR spectroscopy. Again, sensitive means that it can easily be detected. It can easily be found because of its higher natural abundance. Its Larmor frequency is higher, its gyromagnetic ratio is higher, which means its response towards the magnet is higher. It can easily be studied or easily be detected. So you can have very good proton NMR spectrum with a lesser quantity of your sample, but for a good carbon-13 NMR spectrum, you might need larger quantities. As I told you earlier, that when you turn on the magnet, these nuclei, they arrange themselves in all possible spin states and they start precessing with a particular frequency. So we saw the frequencies in the previous slide. Here we have the different spin states. So again, if B naught is equal to 0, these nuclei are randomly oriented. They do not have any specific direction, which means that all of these nuclei are degenerate or they have similar energies. But as you turn on the magnet and you start increasing B naught, you see that an energy gap develops between the two spin states. So they arrange themselves in all possible spin states. For a spin half nucleus, as you can see here, there are 2 possible spin states. One is a lower energy spin state and the other is a higher energy spin state. An energy gap is developed between these 2 spin states, and this del E is directly proportional to B naught. You can see it from this diagram that if B naught is equal to 0, there is no energy gap between the spin states. But as soon as you start increasing the B naught, this energy gap increases. So del E is directly proportional to B naught. And if you convert it into this equation, del E is equal to K B naught. And you also know another equation that del E is equal to H mu. H again is the Planck's constant and mu is the frequency. So del E is directly proportional to frequency. Which frequency? I'll tell you later which frequency is this. But there are a few relationships that you need to understand and remember. The first one was between B naught and omega. So Larmor frequency is directly proportional to B naught. Here, the difference of energy between the spin states is also directly proportional to B naught. So everything till now is dependent upon B naught except for the gyromagnetic ratio. That is independent of B naught. That is a characteristic property of every nucleus. But the Larmor frequencies and the energy gap between the spin states, they are both directly related to B naught. If B naught is higher, del E is higher, omega is higher. If B naught is smaller, del E is smaller, and omega is also smaller. So you have to remember this relationship between these three different quantities. So we have two possible spin states for a spin half nucleus, which we name as alpha and beta states. Here you see that the spin is plus half, and here the spin is minus half. So minus half means that it is against the direction of the applied magnetic field. Plus half means that it is aligned along the direction of the applied magnetic field. And if you take an example of a person swimming in a flowing water. So if you are swimming with the flow of water, that looks easier because you don't have to apply a lot of energy. The flow of water takes you along with it. But if you are swimming against the flow of water, that takes a lot of energy because you have to apply a lot of energy so as to now not allow the flow of water to take you with it, but you struggle to swim against the flow of water, and that takes a lot of energy. And that is why, because in the minus half spin state, the nuclei are aligned against the direction of the applied magnetic field. That means it's a higher energy state, and that is why it is written here. And in plus half state, they are aligned along the direction of the applied magnetic field, so that is a lower energy spin state. How much is this energy gap? And how many nuclei would be in alpha state? And how many nuclei would be in beta state? Is it a 50-50 ratio? Will 50% of the nuclei still be in the alpha state and 50% will go into the beta state? So now we will discuss the population densities of these different nuclear spin states. Now the energy gap that is developed between the two spin states is not very large. There's a small energy gap, which means that both the spin states will be populated. But what will be the relative population, or what would be the population density of the two spin states? Are they equally populated? Let's see. No, they're not equally populated. There always is a small excess of nuclei in the lower energy state, which is also known as the Boltzmann axis. So everything, it tries to be in a lower energy state to be stable, and that is why when you have, for example, 100 nuclei, not 50 of them would be in the alpha state and 50 in the beta state, but there will be slight excess of nuclei in the alpha state. For example, you would have like 52 nuclei in the alpha state and 48 nuclei in the beta state. That might be the ratio. If the energy gap is higher, so you might have 55 in the alpha state and 45 in the beta state. So that energy gap also defines what would be the relative density of population in these two spin states, right? If the energy gap is higher, then the difference of the population in alpha and beta states would be greater. So we have an excess of population in the alpha state, which means that there are slightly more number of nuclei in the alpha state than in the beta state, but because of smaller energy gap, the difference would not be much. But if you increase the energy gap, how can you increase the energy gap? You remember? Yes, increasing B naught, because del E is directly proportional to B naught, which also means that the difference of population between alpha and beta states is also directly proportional to or directly related to the strength of the applied magnetic field. So everything is related to B naught and everything is directly related to B naught. So you increase B naught, del E increases, the difference of population increases, and that means that the excess nuclei or the number of excess nuclei in the alpha state also increases. So what do we have to do with that? Why would we like to increase the number of nuclei in the alpha state, or why would we like to increase the energy, the difference of population between the alpha and beta states? We do need it. Why? Because a higher population difference means a stronger signal. So now you know that if you want a stronger signal, what quantity you want to increase? That is the number of excess nuclei in the alpha state. And how can you increase that? By increasing the energy gap between alpha and beta state. And how can you increase that? By increasing B naught. So you have a higher B naught, energy gap is higher, excess population in the alpha state is higher, that means a stronger signal. What if we have equal populations? And can we have that? Yes, we can. Under special conditions, we can have equal populations in both alpha and beta states. And that is a state we call saturation. Or you can say that the system is saturated. So we have equal number of populations in both alpha and beta states. And that is where we don't get any signal. Just very interesting, right? You just need to remember the relationships between all of these things, and it's very interesting, I think, and it's not very hard to understand or remember these things, because till now what we have discussed, everything is directly related to B naught. Omega is directly related to B naught, Raman frequency is directly related to B naught, del E is directly related to B naught, the population density is directly related to B naught, because population density is directly related to del E, which is in turn directly related to B naught. Right? Okay, let's move forward. Here we have a term that we call the net magnetization vector. See, when you are analyzing your molecule, your compound in NMR, you do not place one molecule in your NMR tube or NMR machine or inside the magnetic field. You have a sample in milligram quantities, and that has a lot of molecules, right? And each of those molecules have more than one hydrogens, more than one protons. So how would you see them? We can see the whole system in a combined way, and that is what we call the net magnetization vector. As I told you earlier, that these nuclei are shown in the form of a vector because they have a particular direction of spin and of course magnitude of spin, so we can show them as vectors. So if we have one nucleus, and this is how it looks like, you can see in the diagram, these are the three Cartesian coordinates, z-axis, x-axis, and y-axis. And this is the nucleus in white, shown as a vector. And why it's shown in this form? Because it is precessing with a particular Larmor frequency. So this is one nucleus. And where is it pointing? It's pointing in z-axis. So again, by default, in all texts in literature, you will find the z-axis pointing up. So B naught by default is pointing up, z-axis is pointing up. So anything that is aligned along the direction of the applied magnetic field, that is in lower energy state. And that is why we say that this z-axis is the equilibrium position for these nuclei. This is the lower energy state. Z-axis or z-axis is the lower energy state for these nuclei. So anything pointing up means pointing in z-axis, right? So this is the nucleus that is pointing in z-axis, but at the same time it is going through this precessional movement with a particular frequency, which we call the Larmor frequency. But what if we have more than one nuclei? And you also know that as soon as you turn on the magnet, not all of them are pointing in z-axis. Some of them are pointing against the direction of the applied magnetic field. Again, by default, B naught is pointing up. So I may not draw it every time pointing up. Now it must be understood to you guys that B naught is always pointing up. So if B naught is pointing up, some of the nuclei you can see they are pointing up, others are pointing down. And at the same time, all of them are also precessing with a particular frequency, which we call the Larmor frequencies. So there's a bunch of nuclei, a lot of them. And you also know another fact, that there is a slight excess of nuclei in the alpha state. So which of these two is the alpha state? This one, yeah. This is the alpha state because these nuclei are aligned along the direction of B naught. These nuclei are aligned against the direction of B naught. That is the beta state. All right. These nuclei down here, they are in beta state, and these nuclei are in alpha state. And you already know that there is a slight excess of nuclei in the alpha state. So which means that the number of these nuclei is slightly greater than the number of these nuclei. Each of these nucleus, whether in alpha state or in beta state, they have a particular magnetic moment. So the magnetic moment of a nucleus pointing up will be cancelled by the magnetic moment of another nucleus that is pointing up in the same direction, in exactly opposite direction. So this nucleus is cancelled out by this one. This is cancelled by this one. So the magnetic moments of all of these nuclei in the beta state are cancelled by the magnetic moment of these nuclei in the alpha state. But you know that there is a slight excess of nuclei in the alpha state. So some nuclei will be left behind whose magnetic moment is not cancelled by nuclei in the beta state. And that is the excess nuclei. And those excess nuclei are shown with this bold vector. You can see this bold arrow here as M naught, or the net magnetization vector. So this is the net result. Some of the magnetic moments are cancelled out. Those in axis are shown here as M naught, and this M naught will always be pointing up in z-axis. Why? Because this is the combination of the excess nuclei in the alpha state. And you know that nuclei in alpha state means pointing in z-axis. So z-axis is the equilibrium position for M naught. So when there is no external energy applied to this M naught or these excess nuclei, M naught actually is the excess nuclei. It's a representation for the excess nuclei. So when no external energy is applied to M naught, it will always be pointing up in z-axis. So this M naught allows us to see the system as a whole, right? Rather than drawing these diagrams with separate arrows or vectors, we draw the net magnetization vector as one bold arrow pointing up in z-axis. So it allows us to see the whole system as a whole, right? So this is how nuclei are arranged, and this is the net result. Remember, everything we do in NMR is to do with the position of this M naught. So the position of M naught is very important. You will see that later on why it's important. So the position of this M naught in these three coordinates, in z-axis, y-axis, and x-axis, is very important, because a different position might give you a different information about the molecule. So whenever you are performing NMR experiment, you should be able to know where your M0 lies at this moment, and that is where you will get the required information if you know the position of M0, right? So this is very interesting. We have different NMR experiments. NMR is a very diverse field. It has a lot of different techniques, and each of these different techniques give you different information, because in every different technique, when we perform it, we have this M0 at different positions, and then when you acquire the data, you will get a different result and different information about the molecule. So it's very important and very interesting as well. Now, if you remember, I told you in the first lecture, in the first slide, when we were talking about, or when we were trying to define NMR spectroscopy, is that we have three words in the name: nuclear, magnetic, resonance. So we have the nucleus. What type of nuclei can be studied in NMR? What is the behavior of these nuclei under the influence of magnetic field? So we have covered almost all of it. So we have a spin active nucleus placed in a magnetic field. It starts precessing and arranges itself in all possible directions. Then energy gap is developed. A population difference is developed between alpha and beta state that gives you a stronger or a weaker signal, or even no signal if there is no difference. So all of these are the behavior of these nuclei under the influence of magnetic field. The third word is resonance. So how resonance would take place? That is when you give it radio frequency. So we have these nuclei, some of them, most of them, pointing up along the direction of B0. So when you turn on the magnetic field, you see that these nuclei arrange themselves in all possible spin states, and energy gap is developed between the alpha and the beta state. Those nuclei that are aligned along the direction of B0, that is in alpha state, when they are provided with a burst of energy, and that energy is in the form of radio frequency. So if you provided energy in the form of radio frequency, these nuclei will jump from alpha to beta state. In other words, they will flip. So they were first pointing up in the direction of B0, now they flip and they are aligned against the direction, or they're opposed to the direction of B0. And this process is known as resonance. Now, which frequency should you provide it? You have the equation here. Del E is equal to h mu. H is the Planck's constant. Mu is the frequency. So del E is directly proportional to frequency. Now this mu shows the radio frequency. So we have another relationship. And this time the relationship is between the radio frequency and del E. And you already know that del E is directly proportional to B0. So what does that mean? If the magnetic field is higher, energy gap is higher, and to make a nucleus jump from this state to this state, you would require higher energy or higher frequency. This is absorption of energy. But why we call it resonance? Again, if you remember, I had told you earlier that resonance happens when we have two equal frequencies. When two frequencies match together, we have resonance. So why we call it resonance? Because this frequency, the radio frequency, has to be exactly equal to the Larmor frequency, so as to resonance to take place. Now, how will you know how much frequency these nuclei need to jump from alpha to beta state? Because, for example, you have a molecule, it is completely unknown to you, it has different protons in the structure. How would you know the frequencies of those protons? Or how would you know that what is the energy gap and how much energy or how much frequency is required to make this nucleus in the alpha state jump into the beta state? How? Because that is exactly equal to the lambda frequency. So, if you know that you are operating at B naught equal to 7.05 Tesla, the lambda frequency of the nucleus is 300 megahertz, which means that how much energy you need to provide it so that to make it jump from alpha to beta state, exactly 300 megahertz. So that radio frequency has to equal this lambda frequency so as to resonate, so for the resonance to take place, and that is when the nucleus will jump from alpha to beta state, because that frequency is directly proportional to del E, and that is also directly proportional to B naught. So you can see that if we have B naught equal to 1 Tesla, the frequency required is 42.6 megahertz. If B naught is 7.05 Tesla, the frequency required is 300 megahertz. Because at a smaller B naught, del E is smaller, the energy gap is smaller, so the energy that is required for nucleus to jump from alpha to beta state is smaller. So the energy that you give from outside in the form of radio frequency should have a lower frequency, of course, yeah. And if B naught is higher, energy gap is higher, you would require a higher frequency radiation for this flipping to take place. So this is what we call resonance. So till now, I hope you have gained enough information about the different steps involved in signal generation. All of these steps are leading us to an NMR signal, but we don't have an NMR signal right now. I'll show you how it is originated, right? As I told you that this mu is directly proportional to del E. Now, we're talking about two different nuclei, proton and carbon-13. Will they require the same radio frequency under the same magnetic field for this flipping to take place if you compare proton and carbon-13? No, because we just saw in that table that protons and carbons, they have different lambda frequencies under the same magnetic field. And they have a difference of almost 4 times. Proton has a 4 times higher lambda frequency under the same magnetic field than carbon-13. So that means the radio frequency required for this flipping will also be different for proton and carbon. But what if we are comparing all the protons in a molecule? You have a molecule and you have more than one protons, of course, more than one hydrogens. Will all of these hydrogens absorb the same energy in the form of radio frequency? We're not talking about, or we're not comparing it with carbon-13, we're only comparing it with other protons. So a proton will it have the same radio frequency or same lambda frequency as all the other protons? That is a very interesting question and very important question. So which frequency is absorbed? I told you earlier that radio frequency matching the precessional frequency of the nuclei under observation is absorbed. So we have one magnetic field, and we saw that under the same magnetic field, for example, 7.05 Tesla, the precessional frequency of proton is 300 megahertz. So will all the protons in a molecule absorb 300 megahertz? That is a question that needs to be answered. No. The answer is no. Not all of these protons will absorb the same frequency. Then why we tell this whole story? It's because of the fact that these nuclei might be in different chemical environments. These protons might be in different chemical environments. You see, these protons might be attached to carbon atoms, they may be attached to oxygens, they may be attached to nitrogens, they may be attached to sulfur, they may be attached to for example, a carbonyl carbon, an sp3 hybridized carbon, an sp2 hybridized carbon, an sp hybridized carbon. So the chemical environments are different. So what does that have to do with the lambda frequency or the resonance frequency? That we will see in a moment. So The amount of frequency that is absorbed by the proton is dependent upon its chemical environment. What does that mean? So we have a nucleus, we have a proton nucleus, and it has certain groups arranged around it, for example, carbon atoms, oxygen, nitrogens, and they will affect these protons. It will have some amount of electron density around it. So there is an electron cloud or electron sea around this proton, depending upon the type of atoms that are present. We will discuss that in the next lecture, not here, but this is just to show you the mechanism, how it happens, right? So we have this nucleus here. It has an electron cloud or electron sea around it. So as you turn on the magnet, this electron cloud will move in a direction. It will start moving in a particular direction because under the influence of this magnetic field, these electrons will move. And you know that the movement of electrons is known as current. And whenever current flows, it produces its own magnetic field. So we have the movement of electrons here. This is from left-hand rule. If your B naught is pointing up, these electrons will move in the direction. If the thumb of your left hand points in the direction of B naught, your curved fingers will show the direction of the movement of these electrons. So you take it as a horizontal electron cloud. B naught is pointing up, and you see that they are moving in this direction counterclockwise, right? But when current flows, magnetic field is generated. You know, the current that flows in the electricity wires has its own magnetic field around it. So we have electrons moving here. That means some amount of current is produced here, and this current then in turn produces its own magnetic field. So we can show it with the help of some magnetic field lines. And this magnetic field that is generated because of the movement of these electrons is known as induced magnetic field, B induced. We call it B induced. And you can see that the magnetic field lines, they also move in a particular direction, and that is from the right hand rule. So if the current, or if the thumb of your right hand points in the flow or in the direction of the flow of current like this, then the curved fingers will show the direction of the movement of or the direction of the magnetic field lines. So you can see that it's moving here, and right in the center these magnetic field lines are pointing down. You can see it here. And similarly here, if this is moving to the right, then again the curved fingers are moving into this nucleus downwards. So this is all around it. These magnetic field lines are all around this nucleus. Now, if the nucleus under study, if your proton is in a region where the magnetic field lines are opposing, or this B induced is opposing the applied magnetic field, it means that it is shielding the proton from the effect of B naught. It's just like a shield which protects you from the attack of your opponent. So these magnetic field lines, which are against the direction of B naught, they are actually protecting this nucleus from the effect of B naught. But if it's in a region where the magnetic field lines are pointing in the direction of B naught, which means that it will reinforce the B naught. It will enhance or increase the effect of this B naught on the proton or on the nucleus. So if it is in a region that is where the magnetic field lines are against, the effect of B naught is diminished. So what actually it gets is B effective, which is a difference of B naught and B induced. So if it is pointing down, it diminishes the effect of B naught. So what it receives as a result is not B naught, but B effective. And this is the effective magnetic field that actually changes its behavior. So every nucleus, every proton, or every carbon does not receive exactly the same magnetic field as B naught, as we are providing it from outside, but its local environment changes the overall strength of the applied magnetic field, and that is what it gets as a result, B effective. So B effective is smaller in a region where the magnetic field lines are opposing. We call it shielded. We say that the proton is shielded from the effect of B naught. That means it receives lower magnetic field. If it receives lower magnetic field, what does that mean? The Larmor frequency is lower. If Larmor frequency is lower, the frequency that is required for resonance to take place will be lower. So it will absorb a frequency slightly lower than 300 megahertz if B naught is equal to 7.05 Tesla. It will not exactly resonate at 300 megahertz, but slightly at a lower frequency than 300 megahertz. But if it is in a region where the magnetic field lines are in the same direction as B naught, then they are actually reinforcing the effect of B naught, which means that B effective would be greater than B naught, because in that case B effective is equal to B naught plus B induced. If B effective is greater, Larmor frequency will increase, resonance frequency will increase, and that might be slightly higher than 300 megahertz if B naught is equal to 7.05 Tesla. And that is why all of these protons might not absorb the same frequency from the radio frequency transmitter. So these were some of the basic things about NMR spectroscopy. As I told you earlier, that luckily we have the same spin quantum number for both proton and carbon-13. So whatever we are studying for proton is equally applicable to carbon-13. But you have to remember the differences. The Larmor frequencies are different. The gyro-magnetic ratio is different. The energy gap is different. And that is why the signal strength is different, because the natural abundance is also different. The next couple of lectures are also very important. So I hope you watch them as well. Thank you so much. See you later.